Okay, in this video, I'm going to look at this example here, where we've got this boundary value problem governed by this ODE subject to these two conditions. Of course, epsilon is a small parameter. The first thing I want to do here is we're going to assume that a boundary layer exists at x equals to 0 as before. Then the outer solution, which should be valid around x equals to 1, is going to be governed as follows. So the leading order, if we let y be equal to y naught plus epsilon y1, etc., then y naught is going to be it's going to satisfy y minus y naught prime plus y naught equal to 0, which is obtained by just setting epsilon equals to 0 there. Since this is going to be valid at the end x equal to 1, then we expect it to satisfy this condition here. Solving this tells us that y naught is simply going to be e to the power x minus 1. Then we're going to do the same thing in the inner region, which is going to be in the neighborhood of x equals to 0. So if we introduce a scaled variable as before, x equals to epsilon to the power alpha xi, and substitute the ODE, becomes going to be epsilon to the power 1 minus 2 alpha y double prime minus epsilon to the power minus alpha y prime plus y equal to 0. Alpha equal to 1 gives the distinguished limit, and so the ODE becomes y double prime minus y plus epsilon y equal to 0 with that condition. Then this time, if we expand y in this form, then the leading order equation of y naught is going to be y naught double prime minus y naught prime equal to 0, subject to this condition here. Solving this gives us y naught is equal to 1 plus a e to the power xi minus a, where a must be determined by matching with the outer solution. If we do that, to determine a, we apply. So the matching equation, of course, y naught xi goes to infinity, x goes to 0. Now, however, this is going to have a problem because this function is unbounded as xi goes to infinity. Okay, so when we try this, we find that matching is impossible because y naught is unbounded as xi goes to infinity. So in fact, this is an indication that the assumed location of the boundary layer is incorrect. So the assumed location of the boundary layer is incorrect. We are going to set up a criteria for deciding the location of the boundary layer in a moment. So right now we need to put the boundary layer at the other end and then solve the problem. So the correct location of the boundary layer is at x equal to 1. So what this means is that if we go back, so our outer region is going to be in the neighborhood of x equal to 0. So at order 1, we're going to have that minus y naught plus y naught equals to 0. And then this must satisfy the condition around x equal to 0. So y naught is actually going to be given by e to the power x. Maybe we can find the solution at order epsilon. So that one is going to be y double prime minus y prime plus y1 equals to 0. And y1 when x equals to 0 is going to be given by that. So if you plug in y naught, this is going to be y1 prime minus y1 is equal to the x. If we solve this, we are going to find y1 is equal to x e to the x. Then for the inner region, which is going to be in the neighborhood of x equal to 1, we are going to introduce a scaled variable. So we're going to introduce a scaled variable according to the equation 1 minus x is equals to epsilon to the power alpha times xi, and then y is going to be scaled to that capital Y. The derivatives then are going to look as follows. So dy dxi dx, this is going to be negative epsilon to the power minus alpha because of this negative sign there. And then the second order derivative is going to be as before, minus 2 alpha, second order derivative of y. So the ODE becomes, so we're going to have epsilon to the power 1 minus 2 alpha second order, and then this term becomes plus, and of course this remains as it is. This is at the end x equal to 1. Now when x equal to 1, xi is equal to 0. So the condition is going to be y equals to 1 when xi is equal to 0. Again, the distinguished limit is obtained when alpha is equal to 1. Okay, and so the equation is going to become y double prime plus y prime equal to 0, and when xi is 0, this is equals to 1. And then, as before, we seek a regular solution of this form. So when we do that, at order 1, we are going to have y naught double prime, y naught prime equal to 0, y naught at xi equals to 0 is 1. And when we solve this, this is going to give us y naught is equals to a plus 1 minus a e to the power minus xi. So the crucial thing here is that in the solution, the power of xi is negative. So we can try matching. Okay, so before we go on, the matching equation is going to be slightly different this time. So the matching equation becomes limit of y naught as xi goes to infinity. Notice that because of this negative here, as x goes from 1 towards 0, xi goes to infinity. Okay, and as x goes above 1, then xi goes to negative infinity. So what we're saying is that if this is x equals to 1, as we go this way, xi goes to negative infinity. As we go this way, xi goes to positive infinity. So our limit is going to be as xi goes to infinity. This should be now x is going to go to 1 because the outer solution is valid at x equals to 0. And so if we let xi go to infinity here, that gives us a. If we let x goes to 1 in the outer solution, y naught, then that gives us e. So that tells us that the constant a is equal to e. So we can plug that one in and then look for the order xi solution, and look for the order epsilon solution. So this is equal to the limit as y naught as x goes to 1. So we've just said a is going to be e, therefore y naught is going to be e plus 1 minus e to the minus xi. Now we go to order epsilon, then the equation we're going to have is y1 double prime plus y1 prime plus y0 equals to 0. y1 at 0 is going to be equal to 0. Substituting y naught, this is going to give us this equation here, e minus 1 to the minus xi minus e. Solving this is going to give us y1 equal to 1 minus e xi e to the minus xi minus exi plus b, an unknown constant, e to the xi minus 1. The matching equation at order epsilon is going to be slightly different from the previous case. So this side is going to be y1 at 1 minus xi y0 prime at 1. This negative again is due to the fact that there is that negative in the relationship between xi and x. So when we do the Taylor expansion here, then the second term is going to have that negative. Now, so on the left hand side here, just let xi go to infinity there. The first term is going to go to 0. This one is just going to remain like that, but be very large. This one is going to give us minus b. Okay, y1 in the outer solution evaluated at 1. Remember, y1 is x e to the x, so that's just going to give us e, and then minus xi y1 prime is just, sorry, y naught prime is just going to be the same as y naught, then evaluated at 1, that's just going to be e. So again, these terms just cancel out, so this tells us that b is going to be negative e. And then once we've obtained b, we can plug it into the solution, and then we have everything determined. After that, we could match the solutions, or rather we could obtain a uniformly valid solution. So in conclusion of this video, we're just going to state the concise condition or criteria for the location of the boundary layer. Right, so given the linear ODE epsilon y double prime plus ay prime plus by equals to c, defined in the range x between a and b, then a boundary layer occurs on the left hand side, if the coefficient of y prime is always positive, the boundary layer occurs on the right hand side. If the coefficient of y prime is negative throughout this region, if the coefficient of y prime changes sign over the region A to B, then a boundary layer will occur at an interior point x0 where A vanishes, and boundary layers may occur at both x and x equals to A and x equals to B. Okay, for the purposes of this course, we're just going to confine our study to these two cases. These ones, of course, if you are interested in this type of thing, we can talk about for research purposes and further study.